Find the number of trailing zeros at the end of 1,000 factorial. Let's start out by writing out 1,000 factorial. 1,000 factorial is 1,000 multiplied by 999 times 998 times 997, and this goes on until you get down towards the bottom. 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. Now, if you were to put this into a calculator, it would overflow, but if you had as many digits as you needed, you would get a huge number here for 1,000 factorial. And furthermore, at the end of 1,000 factorial, you would have a bunch of trailing zeros. That is, this would definitely end in 0 because there's a 10 in here that's being multiplied. In fact, there's 1,000. He would contribute some zeros as well. So the question is, how many of those trailing zeros are there at the end of 1,000 factorial? One way to proceed is to say, well, 1,000 will give you 3 trailing zeros. If you go down to 990, that will give you 1 trailing zero. If you go down to a 980, that'll give you another trailing zero. If you continue with that pattern until you hit 900, well, 900 will give you 2 trailing zeros. And you go all the way down until you hit 10, and there's 1 more trailing zero. Well, the problem with that approach is there's other trailing zeros that sneak in. For example, here's 5 times 2. Well, 5 times 2 will also give you a trailing zero. So that approach doesn't work, but here's one that may not be the first thing that you think of. But you could write the prime factorization of 1,000 factorial. And what will that look like? Well, there will be a certain number of 2's in this prime factorization. I don't know how many 2's there are, so I'll call it A. Where do those 2's come from? Well, we get a 2 right here from 2. We get 2 2's from 4. We get a 2 from 6. We get a 2 from 8. We get a 2 from 10. We get a bunch of 2's from 1,000, right? So that's the first part. Then the next prime number is 3, and I don't know how many of those we have, but let's call it B. And then you'll have 5 raised to the C power, 7 to the D power. Now, 9 is not a prime number, but 11 is a prime number, so you'll have a bunch of 11's in there, a bunch of 13's. 15 is not a prime number, so that does not get included, but the next prime is 17 to the G power, 19 to the H power, and on this goes for each one of the primes. Now, if you look at it in this fashion, where do we get trailing zeros from? We get a trailing zero whenever there is a 2 and 5 pair. That's how we get a trailing zero. So the answer to the problem is actually the smaller of the number A and C. Let's see if we can figure out which is smaller. Do you think there will be more 2's in the prime factorization, or will there be more 5's in the prime factorization? Well, there are so many more even numbers than there are multiples of 5. It turns out C will be the smaller of the 2. That'll be the number of matched pairs, 2's and 5's. So that right there happens to be the answer. So if we can figure out how many 5's are in the prime factorization, we'll have the answer to this problem. So we want to look at all of these factors here, and we want to figure out how many 5's are going to show up in the prime factorization. Well, you are going to get 1 5 in the multiples of 5. And what are those multiples of 5? They are 5, 10, 15, 20, 25, 30, 35, 40, all the way up to 1,000. Okay? So we can count on getting a 5 in that prime factorization from every single one of these guys. In fact, let's figure out how many of those there are. If we take 1,000 and divide it by 5, we will get 200 5s out of these numbers. But actually you get more, because look at 25. We were only counting on him for 1 5, but he actually gives you 2 5s. So you get an additional 5 here in 25, and in fact all of the multiples of 25. So not only does 25 give you an additional 5, so does 50. Because 50 is 5 times 5 times 2. You get an extra 5 out of him. Same is true of 75 and 100, all the way up to 1,000. Now, how many are in that group? Well, if you take 1,000 and you divide by 25, there are 40 more 5s that you get in that particular list. But there is more. There is 1 5 in the multiples of 125. So 125 is 5 to the 3rd power. So for example, that's going to be 5 times 5 times 5. So not only was 125 in this list, 125 also showed up in this list. So it gives you still one more 5. So there's 125 and 250 and 375 and 500. I guess we can go all the way to 1,000 here. This is 625, 750, 875, and 1,000. And you can see that in this case we have 1, 2, 3, 4, 5, 6, 7, 8 additional 5s that show up in that list. Another way to calculate that 8, of course, is we could have taken 1,000 and divided by 125, and that would have given us our 8. Finally, there is 1 5 in the multiples of 625, which is 5 to the 4th power, and in fact there's only one such multiple, and that's 625. The next one, which would be double that, which would be 12,000 or 1,250, is outside of the range from 1 to 1,000. So in that case we just get one more 5 from him. So the value of C here, which is the number of 5s in this prime factorization, that'll show up right here, that turns out to be 249, and 249 is the number of trailing zeros at the end of 1,000 factorial.